Hello, everybody, and welcome to the webinar on the HVAC system. In particular, in this webinar, we will talk about some condensation phenomena that could be related to the HVAC system and how to simulate this system. So, how using simulation tools to treat humid air and understand the phenomena that are in the HVAC system and being able to design this kind of a system. For all the engines of the webinar, there is the possibility to write questions. So I invite you during the webinar to write any question and request in the chat panel of the webinar, and so at the end I will be able to answer to all the questions before the closure of. Okay, so let's start. So just a recap about the HVAC system. So HVAC system can be used for example, to represent data center and processing plants. So are let's say systems that are designed in this kind of situation where the cooling aspects are really important. So it's at the same time important to design in the correct way the HVAC system. Then usually you have to design it for civil and industrial buildings, and these systems are designed for internal air ventilation and to guarantee the comfort of the people that are inside these buildings. And then as let's say secondary lines that are connected to the HVAC system, there are chiller and refrigerator units that are also let's say yes, secondary light, but allow to the perfect work of the HVAC system. So it's something that should be already designed together with the entire HVAC system. So what are the main components of an HVAC system? Usually the system is represented through a process flow diagram, so a PFD, and it's composed by a set of typical components. So there are fan or blowers, ducts, mainly rectangular, but could be also circular ducts, filters, louver and dampers to allow the regulation of the mass flow in the different channels. Then there are also evaporator coils where condensation phenomena take place, and there are then heaters, and there is also in the secondary line the compressor and the related condenser coil. So this is the main scheme that and the related components that you find in HVAC system. So when you design it, you have a process flow diagram, and we will see that in the simulation we try to follow this process flow diagram. The idea is to follow a 1D approach. So solving the fluid dynamic equation, because you have transportation of air, so you have let's say the classical thermofluid dynamic equation, which are mass, momentum, and energy to be balanced, and you can use a 1D approach. So it means that you can just focus on components connected in a network, and this is a really fast way to have a simulation and to be linked and matched to the process flow diagram. So this kind of approach is to focus on the average quantities, because are the main quantities that you that you would like to process and point out. So mass flow, pressure and velocity, and also temperature on a cross section, and you have an average on the cross section, and then you can follow this distribution of pressure, velocity, and temperature across the line, and you can follow the process flow diagram. And you can have also an arbitrary combination of pipes, and you are able to create a really complex network with this kind of approach, following all the path of the HVAC system, just linking all the parts of the system. The benefits that you have with this kind of approach is the fast resolution, because you have just components that could be easily discretized with a mesh, and you have a steady state analysis really fast. So in a few seconds, you have the answer about the mass flow distribution and all the quantities that you are interested in. So in this case, due to the fast resolution, transient scenario are also affordable and can be easily resolved. So the idea of the 1D approach, and in this case we will see a model, so a 1D tool for this that follow this kind of approach, which is Flownex. You start from a real plant, and then, as I said, you have the process flow diagram, and that represents the plants, and then you are able to make one-to-one in the Flownex model, like the PFD, each component for each part of the PFD. So you have the blower, you have the valves, you have the channels, you have the filters or the louver, and so on. So the idea is to have a model that it's practically identical to the process flow diagram. So it will follow the flow, the fluid flow, in this case, the airflow inside the different branches. Just 2 words about Flownex. So Flownex is a 1D CFD tools, so it's able to solve in the 1D approach, so with connecting different components together. It's able to solve really large thermofluid networks with the same equations, so fluid dynamics equations, so mass, momentum, and energy, and you can obtain the distribution of mass flow, pressure, and temperature. In this case, Flownex has a specific library for the HVAC industries, and is able to simulate not only the main line, as we will see, so the main fluid flow, which is humid air, but also the secondary lines with refrigerants and liquid. And it contains a lot of refrigerants, so it can also solve not only the main line but the secondary line at the same time, so in the same system. Then you can also link control tools and control loops that could be inside the Flownex to control valves and regulation, or could be also easily linked also other tools for control system. And just a last remark, and that Flownex has reached a quality of compliance that start from the nuclear verification and validation. So it's a state of standard for this kind of software. So let's have a look at the HVAC library in details. We have special components that are really common in this kind of problems. So we have ducts, vents, and junctions that are already developed for the different shape of the channel. So it can also create cross junction with channels that could be squared or bent with the square profile. But it can also create also circular pipe if there are any in this kind of system. Then you have dampers and obstruction. So you have louvers and butterflies. So you have different kind of louvers and different shapes that you can characterize by a fraction of area of open area that is available to the fluid flow. Then you have heat exchangers, shell and tubes and fin and tube heat exchangers, and then you have fans for the calculation of the chart operating point of the fan. Okay, let's have a look at a first example. So for going more into the details about this kind of system, in this first example, we have an industrial HVAC system that is really complex. You can see that you have an inlet section with a specific mass flow, and then you have secondary lines, then you have fans, you have different dampers, elbow, and a really complex distribution of ducts. So the idea is that you are able to create this real model in Flownex. So you can see that you can put a lot of components and connect together to represent the real diameter of each part of the system, and you can put the fan or blower, and then you have the dampers, and then you have continue with the distribution with the kind of louvers and all the channels. Then you can put boundary condition to represent the exit, and you can put atmospheric boundary condition, and we will see that you have the possibility to set the boundary condition also in terms of humidity. So if the fluid flow is humid air, so is a mixture of air and water, that is the content of water that generally represent then the relative humidity. Then inside this system, for example, first of all, you can calculate and dimension the system. So for example, this is a really similar example to the first one. In this case, you have the possibility to have the sizing of the system. For example, the sizing of the fan. So you are able to select the correct vendor to select the right fan that is not too much for energy consumption, and so you are able to calculate the global pressure drop and the operating point when you select one of the vendor that you can think that is the right one. The input data of the fan are just the curve, so the pressure rise over the volumetric flow rate, and just putting this curve, you are able to calculate the correct mass flow, circulating mass flow, and the operating point of the fan. So here you have just to follow this with more example. You have an incoming flow, you have a cooling coil, you have the fan, you have the supply ducting. In this case, there is an industrial HVAC system that is feeding data center. So you have also an input here. This due to the different servers and machines that are inside the data centers. And then you have the way out. you could be a flow escaping from the room, so you can take into account the part of the area, a fraction of the area, and a small amount of mass flow is flowing out from gaps on the doors, for example, and then you have the main HVAC return line. So the kind of results, as I said, is find the correct fan that you need using the curve of the required pressure rise over the volumetric flow. Then you can characterize also the damper. So we have a look at the detail that you need to simulate. So you put a component which is a damper. You can set the type of the damper. So for example, type of butterfly, and in this case you have the possibility to set the diameter, the angle, and the diameter, the diameter ratio. And so in this case, you have an automatic calculation of the free available area and also the pressure drop that are across the dampers. And the main results that you can obtain are the two different mass flows. This mass flow can be eventually balanced, because one of the main points of the HVAC system is to balance the different branches to provide the same amount of air in the different channels. So you can visualize the flow through the network, so in the different branches, and you can also balance. So this is our other points that you can calculate during the simulation and the introduction of dampers. Then you can make the system more complex, so adding a secondary lines. So with these secondary lines, you have an HVAC, you have an heat exchangers, and you have the two sides of the heat exchangers. This is the main heat exchangers. So this is the main lines. So you have air in this fluid flow, and in this other flow, you could have a refrigerants or water as a secondary lines to cooling the HVAC system. This regulation of the amount of heat that is removed from the HVAC system, and to regulate the condensing part that is happening here, you can also introduce a PID, so the PID, so which is a controller, a standard controller. In this case, this is connected to the speed of this pump, and so monitoring the room temperature, you are able to regulate the speed of the coolants, and you are able to remove a different amount of heat, and at the same time regulate the temperature, so reach the correct temperature set point for the room inside the data center. So here you have the regulation. So you can introduce also regulation with PID, and you can have a loop, a control loop to regulate this kind of system. Then you can pass to a step further on the energy consumption. So you can also characterize the boundary condition in a very special way. So you can also change, for example, with a transient analysis, the weather input data, so the temperature and the relative humidity, try to simulate an entire day or more days to understand what are the energy consumption, because you have different heat exchange due to the external ambient condition, and so you in the different part of the day you are able to have a different energy consumption, and you have a global calculation of the energy that is consumed by the pump and then by the fan of the blower to have the room controlled for at the level of the temperature. So you can obtain the total consumption for the fan and analyze easily the costs that you have. So in this case, you can easily simulate with transient analysis, so transient scenario, changing also the boundary condition that include the main variables of the HVAC system, so relative humidity, dry valve temperature, and pressure. So in this second example, we will see also the condensation phenomenon and how we can treat it. In this civil HVAC system, we have basically the same parts, but now we will focus more on the cooling coils of the dehumidifiers. In the civil system, you have ducts, dehumidifier, heater, humidifier in this case, so the air is also humidified, and this air is provided to offices and then also to a greenhouse. You have this sequence of the humidifier and then the heater, because the air must be firstly dehumidified and then should go back to the right position of content of water, so the final relative humidity and temperature using an heater. So let's try to see how we can simulate this kind of two aspects. So the dehumidifying the process. So you start from the temperature, for example, external air about 32 degrees and 80% of relative humidity, and then you have a cooling power. So this is the part relating to the condensation and a total cooling power that is, in this case example, is fixed to 68 kilowatt, and then you are able to starting condensation phenomena, and then you have an heating power of 40k kilowatt that is in a loop, in a control loop, to be sure to reach the correct temperature or the desired temperature in the part of the offices and room. And then you have the water injection in the latest part for humidifying the air again to go to the greenhouse. In this case, as usual, the fluid is humid air, and so it's air with water which is two-phase. So water is able to be not only in the gas phase, but also in the liquid phase. So it's able to condensate when the temperature is going below the dew point. So looking back at the same system at the level of the scheme, we have a relative humidity from 80% that then is condensated partial of water. Then you reach 40% after the heater, and then you are able to provide this relative humidity to the offices that is already changed due to the amount of heat that is exchanged from the single channels on the external ambient. Using Flownex, you are able to have a look also at the psychometric chart, and you can, as usual, make this kind of calculation and look at the different position about your system, so you can make your loop and have a look in a post-processing which involves the psychometric chart. So this kind of post-processing is already available in Flownex, and you have also a lot of data in each part of the network, which is the relative humidity, the wet bulb temperature, and the dew point. So in each part of the network, you have everything under control, and you can have a look at what are the effects on changing some parameters about the external ambient humidity or temperature, or changing the powers of the dehumidifying process or the heating process. So just to make a focus on the dehumidifying aspects, there is a component that is dedicated that is called liquid water trap, that is used to make the condensation happens. So when the relative humidity reach 100%, so 1, with this component you are able to filter all the condensing water. So the water is condensed, and automatic you have as a post-processing the flow rate of the condensation. So you are able to estimate the amount of water per second of the condensing water. So this is something really useful to understand also over the time what is the amount of water that you are losing from the system, and you are able to see if you can optimize your system and eventually reduce the amount of water that is coming out from the system. This kind of simulation is just to see a real example where it can be applied, that NGSoft has already done recently. Is a plant cultivation chamber, and is a funded research project, and this has followed the same idea of let's say the simulation process. So from plant cultivation chamber, which is a chamber where plants are cultivated and needs to be controlled in terms of temperature, pressure, and relative humidity. There is a process flow diagram which is already been represented in Flownex model, and this model has been implemented as an HVAC system to have a precise calculation of the condition of humidity inside this control room, and so yeah, also be to develop the algorithm to make a control loop and check the temperature and the relative humidity and pressure inside the plant cultivation chamber. So this is the way how you can apply the design of a virtual model, starting from scratch, and then tune your Flownex model to reach the desired condition, and having a detailed calculation about the energy consumption. And moreover, you can be more precise in the selection of the fan or the pumps or the primary and secondary lines to eventually reduce the total consumption of the system. So just to recap for the conclusions, so you can simulate the HVAC system using a CFD 1D approach, so a system simulation approach. Inside Flownex, which is a CFD 1D tools, you have a dedicated library to the HVAC systems that already have the industrial correlation for rectangular ducts and dampers and components, and you can easily introduce all the parts of your HVAC system. You have an interface to create a compact network to check all the input data, and as a post-processing you have the psychometric calculation. So you have the psychometric data and have a post-processing of the loop on the psychometric parts, and as the main results you have in each part of the system the calculation of relative humidity, dry and wet bulb temperature, pressure, and mass flow distribution. And with this approach, you have very quick solving times. So you are able to have answers in a few seconds for parametric analysis and for doing transient scenario. As we have seen, you are able to do something which is transient, changing the weather conditions or the power inside um, inside the heater or the dehumidifying aspects. Okay, so while I have a look if there is any questions, I will just show in a minute the interface. So the system that we have seen we have is this one, and for example, just to show you that you can perform transient analysis, you can load a first step and then run the system, and then you can make an interaction. So you can see that there is an interaction. For example, I can change the power of the humidifying aspects, or I can change a fraction opening of the part in the distribution of the louvers, and I can reach with the control loop the temperature that is designed and calculate the total heat exchange. Okay, so I just answer to the one of the question, which is if there are other libraries other than the HVAC system. Yes, in Flownex there are different libraries that are dedicated not only to the HVAC system, but for example, one is dedicated to the heat exchangers, and moreover, Flownex can use as a general tools. So there is another one dedicated to containers. So it can use as a general tools for application not only with humid air, but also with other fluids, other gas, and other liquids. Okay, let's see if there is any other questions. Okay, I think no other questions. Okay, we can close the webinar here. Thank you very much for following this webinar.